afternoon, everyone. Good afternoon, everyone.
Never talking, just keep walking. Nothing is magic.
Just a midterm is fine.
Everyone's happy when the wizard walks by. Never talking, just keep walking. Nothing is magic. Sun is shining, time to come by. All the people, the happy side. We are prospered, giving it sign. And all the people, it is so fine. Never talking, just keep walking. Let it magic.
How are we doing? The connection seems a bit laggy today. We've had issues in my previous class. So if we get disconnected, I'll restart a new session. Questions before we begin? Anybody? Today's music brought to you by Black Sabbath, The Wizard. Our goal for today is to extend or to present an alternate approach to solving linear programming problems. Blake, if you can tell me what number 11 is, we can discuss it. So, yeah. Right now, I mean, last time we saw the graphical method, which allows us to solve linear programming problems graphically by just considering the vertices of the feasible set. If your linear programming problem has an absolute max or an absolute min, it must occur at one of the vertices. And that's all well and good in 2D. But as soon as you move to higher dimensions, you're in big trouble. So what do? We have another approach. Known as the Simplex method. So the Simplex method will work in all dimensions. So it doesn't have to be 2 dimensions. We don't have to graph anything. Simplex method works, but we'll see that we have some issues with that there as well. We start by considering what is known as the standard maximum problem. So let's define that. Definition. A linear programming problem is said to be in standard maximum form if the following conditions are met. 1, the objective function is to be maximized. Let me finish writing down what the standard maximum problem is, and we'll consider Blake's issue. The objective function is to be maximized. 2, all variables are non-negative. In other words, all the variables are bigger than or equal to 0. What is written after maximum? Form, standard maximum form. Special case of linear programming problems, right? Because, I mean, we've seen these linear programming problems. Sometimes you want to maximize, other times you want to minimize. Here, I'm defining the standard maximum form, where the objective function is to be maximized. All variables are non-negative, and all other constraints are of the form a1 x1 plus a2 x2 an xn less than or equal to b, where b is bigger than or equal to 0. Back to Blake's question though. We are looking for a 3x3 matrix. So, just write out a general 3x3 matrix. A, B, C, D, E, F, G, H, I. If you multiply that by the matrix 1, 0, 0, you should be getting 1 minus 2, 4. But what happens when you multiply these two things together? First row times first column. Second row times first column. Third row times first column. And now these 3x1 matrices are equal. And as Annie points out, you get the first column, right? In order for these to be equal, A has to be 1, D has to be minus 2, G has to be 4. So 1 minus 2, 4. And then do the other two. You're good to go. So nothing is assumed. We didn't know what the matrix was. We called it A, B, C, D, E, F, G, H, I. And you solve. All right. All other constraints of this form. And where are we going with this? The idea is the following. We're going to transform these inequalities into equations by introducing a slack variable. As the name suggests, it's a variable that picks up the slack. Let's illustrate. Suppose you had an inequality, 2x plus 3y less than or equal to 10, right? So an inequality of this form. This is just an example. Does that consider the other constraints? I mean, I'm saying that all the constraints have this form. So this is a very specific type of problem, right? One where the objective function is to be maximized. All the variables are non-negative and the other constraints have this form. Consider this. So clearly, if x is 1, so if x is 2 and y is 1, this satisfies, right? This is 4 plus 3 is 7, and 7 is less than 10. Well, I mean, Blake, we only did the first one, but I mean, you obviously see what's going to happen for the second and third, right? Observe what happens when you multiply by 0, 1, 0, and then 0, 0, 1. So we only did a third of the question, but now I want to claim that you see what's going on. Here, observe that if x is 2 and y is 1, this satisfies the inequality. But, I mean, what do you get? You get 4 plus 3 is 7. So 7 is strictly less than 10. What we're going to do is we're going to introduce a slack variable. Let's call it S1, which is bigger than or equal to 0, so that this inequality, by adding this slack variable, becomes an equation. So in the case that x is 2 and y is 1, S1, right? 4 plus 3 is 7. S1 would be 3. So it then then S1 is 3. If X is 1 and Y is 1, this is 2 plus 3, that's 5. S1 is going to be 5 as well. So that 5 plus 5 is 10. If X is equal to 2 and Y is equal to 2, 4 plus 6 is 10. In this case, S1 is 0. And so on, right? So instead of working with inequalities, we can pick up the slack by introducing a slack variable S1, which transforms, so S1 is called a slack variable, it transforms an inequality into an equation. It's there to pick up the slack, right? In the case that you had something strictly less. So, given a standard maximum problem where we want to maximize an objective function, we're going to transport everything into an array very similar to a matrix, but called a simplex tableau. And we're going to do some row reduction, but not in a way similar to matrices, but rather with respect to an object called a pivot. And I think the best way to really explain what's going on is to illustrate with an example. So let's take this example. Now, first of all, observe that this is a question in 2D, and I've chosen this one for obvious reasons because we'll be able to verify our answer using the graphical method. So that's going to be interesting here. And we'll see the interplay between the simplex method and the graphical method. But before we do anything, let's convince ourselves that we are dealing with a standard maximum problem, because the simplex method, as we're going to describe it, only works with the standard maximum problem. So is this a standard maximum problem? The objective function is to be maximized. Right, so we want to maximize this. First condition is met. All variables are non-negative. Second condition is met. And all other constraints have the form of a combination of x and y less than or equal to something bigger than or equal to 0. Combination less than or equal to something bigger than or equal to 0. Exactly what we have here. This is in standard maximum form. Everybody comfortable with that? Now, think about this for a moment. You want to maximize this function. You want to maximize this function. This guy X is giving you $5 every time you see him versus $2 from customer Y. What are you going to focus on? You're thinking to yourself, well, I'm hoping to see X much more than Y, right? I'm going to try to seek X out. Indeed, you would, right? So we're going to try to focus in on X and see how much we can get out of X. If there's stuff left, we'll go with Y. Right? If we have time left, then maybe we'll focus on Y. But we're going to maximize our time, at least a priori, right? We're going to try to maximize our time by focusing in on X. So let's rewrite this function by bringing the X and Y to the other side. So we're going to have a minus 5X minus 2Y plus Z equal to 0. And let's introduce slack variables to transform the inequalities into equations. So we have two inequalities. We're going to introduce two slack variables. Let S1 and S2 be bigger than or equal to 0, which transforms this inequality into an equation and transforms the other one into an equation as well. And now we're going to put everything into an array called a simplex tableau. We'll reserve the first column for the x's, second column for the y's, third column for the s1s, fourth column for the s2, fifth column for the z, and then the equal stuff. So first equation is telling us 2x plus 4y plus s1 is equal to 15. So 2x plus 4y plus 1s1, no s2, no z, is equal to 15. Second equation, 3x plus 1y, no s1, 1s2, no z, is equal to 10. And the last equation is reserved for your objective function, minus 5x, minus 2y, no s1, no s2, 1z is equal to 0. Now, as Lance suggested, we want to focus in on the x, because it's the x that's giving us the best return, if you will. So, right, because it's 5 versus 2. In the simplex tableau, this corresponds to the most negative thing, most negative entry in the last row. So if we focus in on the most negative entry in the last row, our pivot is going to live in this column, right? We're focusing on the x. So we're going to try to maximize the x's that we get. But now look at this. Look at your equations. How large can x be? Right? You know that y is bigger than or equal to 0. So at worst, this is going to be 0. So x is going to be at most 7.5 and simultaneously at most 10 over 3. So our pivot is going to be the smallest of these quotients. 2 over 5. 15 over 2. Where did that come from? 15 over 2 or 10 over 3. The smallest quotient is 10 over 3. That is our pivot. We're going to do operations based on this number. This is going to be our pivot. All the operations have to come from this element. And we're not allowed to change it using the other rows. The only thing we can do is divide here. So I'm going to change my pivot to a 1. 1/3 row 2 for row 2. So 1/3 row 2 for row 2, what do we get? So how do we find the pivot? We had inequalities, right? So first of all, let me tell you how to find the pivot, and then we'll explain what's really going on. The pivot is going to live in the column corresponding to the most negative number in the last row. So most negative number, -5 is the largest negative. The pivot lives in this column. Two things. The pivot cannot be negative and cannot be 0. So we stay away from negative numbers or 0. We don't have them here, so no issue. Then take the quotient, 15 divided by 2 versus 10 divided by 3. Smallest quotient determines the pivot. 10 divided by 3 is 3.33. 15 divided by 2 is 7.5. 3.33 is the smallest. That's your pivot. 3 is the pivot. And we're going to do row operations based on this pivot that we have changed to a 1. Why are we doing this? Your original function, you wanted to maximize 5x plus 2y. We're going to start by maximizing the variable with the largest coefficient. When you bring everything to the other side, it corresponds to the one with the largest negative number. Then we had two inequalities, 2x plus 4y less than or equal to 15, or 3x plus y less than or equal to 10. How large can x be? Well, since y is bigger than or equal to 0, if you just remove these, x has to be less than 7.5, and x has to be less than 3.33. So x has to be less than 3.33. We focus in on that, the smallest quotient. Right? Because you need x to satisfy both inequalities. So it's that second one which governs everything. We changed it into a 1, looking good. Now we're going to use this 1 to clear out the column. Right? We're doing operations based on this pivot. An excellent question, George. What if the quotient is the same? Right? What if you had two quotients the same? Or you had two minimums the same? Let's define a rule that you will take the topmost. Similarly, what if you had two -5s in the last row? Then which column would you take? Let's define it again, leftmost. So leftmost, if you have the same largest negative, topmost, if you have the same smallest quotient. All right, we're using our pivot to clear out the column. So 2 minus 2, 4 minus 2/3, 1 minus 0, and 45 minus 20, so 25 over 3. And similarly, this plus 5 times that, this plus 5, so minus 6 plus 5. All right. And we repeat. Largest negative in the last row. Largest negative in the last row. Our pivot is going to live in this column. This divided by that. So that's 25 over 10, 2.5. This divided by that is 10. Smallest quotient, 10 over 3. This is our new pivot. This is our new pivot. Let's change it into a, what do we want to do? Well, let's change it into a 1. 3 over 10, row 1 for row 1. What is it that we're looking to do after we find the pivot? Clearing out the column. How do we find the new pivot? Same thing. Most negative number in the last row. Here we only have one, so it's minus 1/3. The pivot is going to live in this column. This divided by that versus this divided by that. The smallest quotient determines the pivot. And now that we have changed our pivot to a 1, we're going to clear out the column. Row 2, minus 1/3 row 1. Row 3, plus 1/3 row 1. So this minus 1/3. This minus 1/3. So 6/15. I want to say 2/5. This minus 1/3. So 20 minus 5, 15/6. It's 5/2. I think it's 5/2. Can somebody verify that? And 0, 0. Here I'm adding 1/3. So 1/10. 1/3 of that. So 25 minus 1 is 24/6. Which is just 4. Is that correct? Five over 6, so 105. No, yeah, 105/6. So, is that correct? All right. Should the 5/2 be a 5/3? That could very well be the problem. This 5/2 is 25/10. No, I think it's 5/2. I think it's 5/2. Did you mean this one here? Well, we'll see. Going under it. So that was 10/3 minus 5/6. So 20 minus 5 is 15/6. 3 times 5, 2 times 3, 5/2. I want to say 5/2 still. Well, we'll see, because we'll redo this question the graphical way, and we'll notice something very nice. But first of all, so assuming this is right, is this right? Anybody have this? Assuming this is right, what now? Well, most negative number in the last row right? I mean, if we continue on with our process, most negative number in the last row, well, now there is no negative number in the last row. So that's it. There is no more negative number in the last row, so we are done. This is the final simplex tableau. We should be able to read off the answer. X has a leading 1. X is 5/2. What, right, so remember this X, Y, S1, S2, Z. Y has a leading 1. Y is 5/2. S1 does not have a leading 1. S1 is 0, right? So now it differs a bit from matrices, but you would have expected that, right? Because this is not a matrix, but rather a simplex tableau. S2 does not have a leading 1. S2 is 0. Z has a leading 1. Z is 105/6. So somehow I feel these might not be correct. Have we made some addition mistakes somewhere? Let's recall what the original question was. The original question was Z equals 5x plus 2y, where 2x plus 4y well, I mean, 104/5, this simplifies, right? 3 divides this. So 3 times 35. So this is really 35/2. Should the 4 be 8/5? Yeah, I think we'll be fine. We'll see. We'll see. Right? This was the original question. So if x is 5/2, this is 5 plus 10 is 15. So there's no slack, right? They're equal. So S1 is 0. 15/2 plus 5/2 is 20/2, which is 10. Again, no slack. So S2 is 0, looking good. And 25/2 plus 10/2 is 35/2, exactly the answer we had over there. So as Bruden points out, there is no reduced row echelon form here. There is no switching of columns, of rows rather. This differs slightly from row reduction, but this is the simplex method, not reduction of matrices. There's a very similar approach, but here we base everything on pivots, not reduced row echelon form. So what we have seems to agree, but now let's do the graphical method and see what's happening, because it's very nice. It's very nice to see what's happening. So let's rewrite these as in a way we can deal with. -1/2 x plus 15/4. And here, minus 3x plus 10. I don't want to erase anything. because I want to point out what's happening. I guess we can erase this one here without too many issues. And let's graph these things. So maybe let's start with the second one here. Minus 3x plus 10. It starts at 10. It goes all the way to 10 over 3. We know everything is bigger than or equal to 0, so there's no need for me to go down these things. And then 15 over 4, that is pretty small. And by the way, we are already restricting our attention to this region, right, because it is an inequality. Or rather the other one. This is 15 over 4. Still negative slope, but it crosses the x-axis at 15 over 2, which is 7.5. So right here. And again, it's the stuff underneath. So this is going to be our feasible set. Uh, 8 over 5, the 4 should be an 8 over 5. You're right that it doesn't influence anything, but I mean, if that's what it should be, we are doing row 3 plus a third row 1. So 5 over 3 plus a third, so minus 1 over 15. So this is 24 over 15. 3 times 8, 3 times 5, 8 over 5, thank you. The 4 is an 8 over 5. Thank you, everyone. Absolutely. Right, so this is our feasible set. Let's work out the point of intersection when minus 1/2 x plus 15 over 4 is equal to minus 3x plus 10. Do we want to multiply everything by 4? So we get a minus 2x plus 15 is minus 12x plus 40. Bring this to the other side and we get 10x is equal to 25. X is equal to 2.5 or 5 over 2. So when x is 5 over 2, when x is 5 over 2, this is 10 over 4, which is 5 over 2 again. Right, so that is our feasible set. Let me erase this business. There it is, with, of course, the origin as a point right here. And we had our objective function to maximize is this. I can now remove this business. And let's observe what is really happening here. Right? I mean, if you start at 0, of course you get 0. And I've erased the first Simplex tableau that we had, but if we recall what it was, what was it? Our first Simplex tableau, I want to say 2, 4, 1, 0, 0, 15. 3, 1, 0, 1, 0, 10. And minus 5. I want to say that this is what we had, right? Where this is x, y, s1, s2, z, right? So suppose that you read this off as we read that one off. X doesn't have a leading one, so x is 0. Y does not have a leading one, so y is 0. S1 has a leading one, S1 is 15. S2 has a leading one, S2 is 10. Z has a leading one, Z is 0. What's happening? X is 0, Y is 0, so Z is 0. Right? X is 0, Y is 0, and Z is 0. You're starting right here. In your simplex tableau, you're starting right there. You're finding your pivot, which corresponds to maximizing the X. So taking Y to be 0, right? What's going to happen? We're going to move to the largest X possible. We're maximizing the X variable here, right? We did our pivot operation. We got to this tableau. Let's read off what this is saying. Again, this is X, Y, S1, S2, Z. X1, X has a leading one. X is 10 over 3. Y does not have a leading one. Y is 0. S1 has a leading one. S1 is 25 over 3. S2 does not have a leading one. S2 is 0. Z has a leading one. Z is 50 over 3. Right? We have moved to the point 10 over 3, 0. 10 over 3, 0. And Z at 10 over 3, 0. What is that? Well, Z is this. So that is 50 over 3. Exactly what this tableau is telling us. But this is not the final simplex tableau because we still have a negative in the last row. So we do another pivot operation, blah, blah, blah. We get to this, where X is 5 over 2, Y is 5 over 2. We have moved to this one. And Z at 5 over 2, 5 over 2. What is that? This is 25 over 2 plus 10 over 2 is 35 over 2. That's what this is telling us. That's apparently our maximum. But in the graphical method, we still have to check this vertex. But the simplex method is telling us that nothing's going to happen here. But let's just see nonetheless. When X is 0 and Y is 15 over 4, this is 15 over 2, 7.5, but that's a lot less than 35 over 2. So that's what's happening in that simplex tableau. You're actually cycling through the vertices until you reach the optimal one. Optimal one guaranteed by the fact that there are no more negatives in the last row. Will the slack variables always be 0 at the end? They will not. In general, you may have non-zero slack variables. How are we doing here? Shall we consider another example? And of course, the point is that this extends to higher dimensions. Dimensions where the graphical method no longer works. Britton, I'm not sure what you mean here. Is that not what we did? In the 2D example? Britton is asking if the slack variables are greater than 0, how would they be integrated into our solution? Short answer is you might not need to integrate them. In the sense that unless otherwise stated, what is this question asking you for? It's asking you for the maximum the function achieves. So maximum would be 35 over 2. Perhaps where that occurs, so at the point 5 over 2, 5 over 2, they could take it up a notch and ask what the slack is. And I think they do that on the web work. But if they don't ask for it, doesn't matter. Let's take this example. Maybe that'll occur here, and we can discuss it then. First of all, observe that this linear programming question is in standard maximum form, right? The function needs to be maximized. The variables are non-negative, and all other constraints have a combination less than or equal to something positive, bigger than or equal to 0. Well, xi is a shorthand way of saying x1, x2, and x3. So if xi is bigger than 0, that means x1 is bigger than 0, and so is x2, and so is x3. Really, the condition for the function, for the problem to be in standard maximum form. So again, right, I mean, here the point is, it's a question in 3D, so the graphical method does not apply here. So let's answer this question using the simplex method. We're going to introduce slack variables Let S1 and S2 be bigger than or equal to 0 such that your first inequality plus S1 is equal to 10 and is equal to 8. And bring all of these to the left so that minus 8x1 minus 10x2 plus 7 minus 7x3 plus z is equal to 0. And then we're going to rewrite this in an array known as a simplex tableau, where we'll reserve the first column for the x1, x2, x3, s1, s2, z, and the equals. So first equation, 1x1 plus 3x2 plus 2x3 plus 1s1 is equal to 10. And second one, 1, 5, 1, 0, 1, 0, and 8. And then combine with this third one here, minus 8, minus 10, minus 7, 0, 0, 1, 0. All right. Most negative entry in the last row is negative 10. Our pivot is going to live in this column. Again, the pivot cannot be negative, nor 0. How do we choose it? Smallest quotient. 10 over 3, 8 over 5, and he suggests the pivot is 5. Absolutely. Again, all operations must be made from the pivot. Let's use this 5 to get rid of that 10 while we're here. Row 3 plus 2 row 2 for row 3. And then change it to a 1. 1 over 5 row 2 for row 2. So row 3 plus 2 row 2, this plus 2 times that, this plus 2, this plus 2, this plus 2, this plus 2. All right. We're not finished, right? This is our pivot here. We're going to use that to get rid of the 3. Row 1 minus 3 row 2 for row 1. Before I erase this, let me point out, what are we doing? We're concentrating on the x2. right? We're trying to maximize what's going to come out of that. But, you know, you're going to do this operation and you recognize that you're still going to have negatives in the bottom. So you're going to be choosing a different pivot. And think about what's happening here, right? The x2 is not very large, right? X2 is at most 8/5. Whereas the x1 could actually be as large as 8. So this x2 is going to be very small, less than 2, versus an x1 which could be as large as 8. So you see what's going to happen, right? Quickly, we're going to forget about this x2 and concentrate on either x1 or x3. I mean, you don't have to make a conscious decision about that. The Simplex method does everything for you, but geometrically, that's what's happening. Right, let's do that. See where that takes us. So roll 1 minus 3. Uh, 10 minus 3 is 7. Fifteen minus 24 is 26/5. I mean, you recognize, I'm sure, that we've got lots of fractions here in the row reduction. We try to leave the fractions until the end, but here we don't have that luxury. All right, so we've done our pivot operation. We changed the pivot to a 1 and we cleared out the column. Excellent. Let's find our new pivot. Most negative number, -6. Pivot is going to live in this column. Smallest quotient, 26/2 is 13 versus 8. 13 versus 8. So we know that the pivot is 1/5. Oliver is asking what happens if we don't find the pivot, then all of this breaks down. All of this breaks down. If you're just haphazardly row reducing, how do you know that it's going to be the maximum? You don't. One over 5 is our pivot. Let's change that into a 1. Actually, maybe you want to get rid of that 2 there. Let's say row 1 minus 2 row 2 for row 1. And then perhaps a 5 row 2 for row 2. So this minus 2, this minus 2, this minus 2, that will be a 5/5, which is 1. This minus 2, this minus 2, this minus 16, that's 10/5, which is 2, Now, I know what you're thinking. Asma will answer that after this question. But I know what you're thinking. If you're taking a step back and you're you're looking at this second row here and you're thinking to yourself, well, we had that second row right here. Isn't what we're doing undoing the work we did in the first part? And indeed it is. Thank you. And indeed it is. Indeed it is. We are undoing what we did in the first pivot operation, and that happens. That happens, right? We concentrated on the 10x2, trying to maximize the x2, but then quickly noticed that this wasn't leading us to the right answer. So we changed our minds. This is our pivot. Let's finish that operation. Row 3 plus 6, row 2 for row 3. This plus 6, 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 and this plus 6. So that's 48, 58, 59, 60, 64. How do we know when to stop? An obvious question. If there are no more negatives in the last row, you're done. If there are negatives in the last row, but then you cannot choose a pivot, because that could happen too, right? And you focus in on the most negative number in the last row, and the pivot lives in that column, but the pivot cannot be 0 nor negative. And if these were 0 and negative, you could not choose a pivot. In that case, there would be no maximum, right? There would be no maximum. The function would not achieve a maximum on the feasible set. There would be no solution. But if you're able to get the last row without any negatives, then this is the final simplex tableau, and we can read off the solution. Again, remember this was x. So we're in that situation right now, no more negatives. This was x1, x2, x3, s1, s2, z. So what's happening? x1 has a leading 1, x1 is 8. x2 does not have a leading 1, x2 is 0. x3 does not have a leading 1, x3 is 0. s1 has a leading 1, s1 is 2. s2 does not, s2 is 0. And finally, z, when you write it here, z has a leading 1, z is 64. Thank you, Aini. Let's recall what our question was to see if this makes sense, and we'll talk about the slag business, which had occurred previously. We were trying to maximize this subject to right? This was our original question. As was saying, let's say that the number was negative and we needed to pivot. Can we do no? What? No. No. No, 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 no. There's no multiplying the row by a negative number. No. No. I mean, all the row operations have to come from the pivot. And what you're suggesting there, right? So, I mean, in case you didn't realize, as Asma was saying, what if this was negative? Couldn't we just multiply the whole row by -1, thereby changing this -1/5 to a +1/5? The answer is no. All operations must come from the pivot. And here you don't have a pivot yet before choosing it. So you're not allowed to do that. Let's look at our answer here. If x1 is 8 rather, and x2 and x3 are 0, then z is 64. So that makes sense. And if x1 is 8 and x2 and x3 are 0, you see that 8 is less than 10. And there you have the slack, right? You have a slack of 2. That's why your S1 is 2. It doesn't play a role in the actual answer, right? This is maximized. The maximum is 64 when x1 is 8, x2 is 0, and x3 is 0. But it plays a role when you look at the actual inequality. You had some extra space here. You had an extra 2 that unfortunately you cannot use. But in the second one, there is no slack, right? 8 plus 0 plus 0 is 8. So you have a slack of 0 in the second inequality. It's a very nice process. And especially when you can make a parallel with the graphical method and you see yourself cycling through the vertices until you end up on the right one. It's very nice. How are we doing here? Asma was asking the logic in needing to find a pivot, right? The idea is, remember, what did we do? We started by saying we were going to concentrate on x2 because it's the one with the largest coefficient. But how large can x2 be? x2 can be at most 10 over 3 and at most 5 over 8. You're bounded by these inequalities, right? x2 cannot be as large as you want. In fact, it's very small. It cannot be bigger than 5 over 8. And so you have to take that into account. That's what the pivot does. Britton is asking if the slack variable doesn't change anything. What does it mean? Well, I mean, compare your answer with respect to the first inequality, right? 8 plus 0 is less than 10. You had that extra wiggle room, that extra slack that might have been useful, but it wasn't. So if these are number of hours, say, available, you could decrease that down to 8 and you'd be fine. That's what we're saying. You have this extra wiggle room, this extra slack of 2 that you could get rid of. Potentially, I'm not saying that you necessarily have to, but yeah. So that's the idea behind the pivot, right? I mean, by focusing on one of the variables, you have to keep in mind that it cannot be too large. You have this boundedness, right? X2 is at most 10 over 3, but also at most 8 over 5, and it's this 8 over 5 which governs everything. So that's why we take the smallest quotient. How are we doing here? Questions? Anyone? Looks like a good place to end. Try this Simplex method. We'll pick this up again on Thursday. Thank you all for coming, and I'll see you guys then.